In the last segment, what we did is we came up with an equation for the surface forces on a fluid element due to pressure, and we're deriving a hydrostatic equation. What we're going to do now, we're going to take a look at the other forces that could be on that chunk of fluid. So there are a couple of other forces that can exist on the chunk of fluid. First of all, we have body forces. And one of the most common ones is gravity, or the gravitational body force. But we could have others. There could be electromagnetic. Or other forms of body force. And what we'll do, we'll look at the gravitational body force here, because that's the most common one. Within fluid mechanics, and I'll write out the gravitational differential force element as being that, and then that is just rho times g, g being the gravity vector, multiplied by the volume of our fluid element. And remember, before we were doing force per volume, so I will write that as a small f, and that would then just be rho times the gravity vector g. Now, the last force we're going to look at is one due to viscous shear stress. And we'll see more of this later on in the course. But for now, just for the sake of completeness, we will include it. And if you recall from an earlier lecture where we talked about Newtonian flow, this, in a way, the term that I'll show you, is similar to the mu du dy, which was giving us the shear stress within a fluid element. And for three-dimensional fluid flow, what we can do, we can write out an equation, and I will put it as Vs for viscous shear. So that is the term for viscous shear, and viscosity is our proportionality constant. And we will express that as del squared V, the vector form of V. So with that, we have the other forces that can be acting on our fluid elements. So what we're going to do, we're going to combine those all together now. If you recall earlier, this is what we had for the pressure. We had the gradient of pressure was the surface force. And then we have this new force here and this one here for the body force and the viscous shear. Let's put those all together, and we will sum forces. On the left-hand side, I will put rho A. And this is force per unit volume, recall. So the left-hand side is MA divided by volume gives us rho A. And on the right-hand side, this will be equal to minus the gradient of the pressure field plus rho times the gravity vector plus this viscous shear stress, or viscous shear force that we talked about. So we can rewrite this now. And this is the most general form of fluid static equation. What we'll be doing, actually, it would not be fluid static because we have the velocity term here, and so you could have velocity field, but we'll make some simplifications in order to get rid of that I'll talk about shortly. But in this equation, so what we can say is that if you know your acceleration vector, so there, and if you know the velocity vector, which is there, you can determine the pressure distribution in the fluid. So that's essentially what that tells us. We're now going to consider a number of special cases of this equation, and these are the ones that we typically use when we're dealing with hydrostatics. So special cases The first one would be if the flow was at rest or constant velocity. So if the flow is at rest, the acceleration vector A is going to be 0, and del squared V is going to be equal to 0 as well. So if we look back at our equation, what we end up with is just grad P is equal to rho times G. And this would be the special case, or the hydrostatic, which we'll look at more extensively in the next segment. So that's the hydrostatic condition. Another special case that can exist is if you have rigid body, translation, or rotation. That would be where the fluid is moving, but it's all moving as a solid body movement. So there's no relative motion within the fluid. All of the fluid particles are moving together. For example, you put all the fluid in a bucket and you move it. For that, what happens is we get grad P is rho times G minus A. That would be the form of the equation for that type of scenario. And the last one that can exist, this is if you do have fluid motion and velocity, but let's say the fluid motion is what we call irrotational. So irrotational motion is characterized by del cross V equals to 0. And with that, what would happen is our grad squared V term would disappear. And consequently, we have another simplification of the equation. Looking back, it's very similar to the solid body rotation one. But with that one, we would determine the pressure. Because we have fluid motion, pressure would be determined using an equation that we'll look at later in the course, which is called Bernoulli's equation. So pressure via Bernoulli equation, that provides the pressure in the equation that we have. So those are simplifications that you can have. In this section, however, we're mainly going to look at the hydrostatic condition and the rigid body translation rotation. We'll look at the other ones later on in the course.